This video is part 3 of molecular structure and bonding, and it just considers a few things that are going to affect bonds. Two aspects of this are electronegativity and atomic size. So just to refresh your memories, the definition of electronegativity is the measurement of an atom's ability to attract electrons from a neighboring atom to which it is bonded. We definitely see an effect of electronegativiity on bond length and angles, and we find that atoms that have large electronegativities are going to draw electrons away from the central atom, and thus it's going to reduce the repulsive effect of the bonding electrons. With atomic size, we find that larger atoms take up more space, so there's going to be an effect on the bond length and the bond angles. In general, the electronegativity is going to win in cases where the electronegativity and atomic size have opposing effects. So in this slide, what we see is a table that shows the bond angles and the bond lengths for a variety of compounds. And you're going to see some trends which are going to be evident on the following slide. So you need to have a look at what you're seeing over here, for example. So in this case, we've got a trend where we're going down a group with a central atom like that. So we start with oxygen over here and we end with tellurium over here. And have a look at what happens to the bond angle. You see that the bond angle decreases as that atom gets larger, and the bond length gets longer as we increase the atomic size. And remember that the electronegativity also changes. Okay, so there's a whole lot of different trends that are evident in this particular slide, which you need to pay particular attention to. Okay, so with the trends that you're seeing, when the central atom is the same and the atoms on the outside bonded to that central atom change, then the atom with the larger electronegativity is going to draw the electron away from the central atom. You're going to reduce the repulsive effect, and you're going to see large bond angles. And as the size of the outer atoms also increase, you're going to see larger bond angles. All right, now what happens when we change the central atom and we keep the outer atoms the same? Again, the central atom that has a larger electronegativity is going to draw electrons away. We're going to see larger angles. But now, when we have a look at the central atom increasing in size, we're going to see a decrease in angle, which you should have picked up on the previous slide. I can probably go back to the previous slide. Okay, no, I can't. But if you go back in the video, you'll see what I'm talking about. So molecules containing hydrogen don't show too much of a trend. And in fact, sometimes the effects seem to counterbalance one another. But in general, we find that these trends do exist. All right, when we know about the effect of electronegativity going from left to right across the periodic table, it increases quite substantially, as you can see from the diagram on the right-hand side of the slide. We find that the early transition metals are electropositive, and they will have very high oxidation states, and they can also be very easily oxidized. While the late transition elements, or metals, which are the ones on the right-hand side, towards the right-hand side of the periodic table, they're quite electronegative, and they're generally found in low oxidation states. So if you think about vanadium, for example, in period 3, it has a significant number of oxidation states, as opposed to zinc, which only has 2 oxidation states. What we find is that the back donation of electrons as you're going from left to right is not so prevalent, and the ligands that are bound are generally subject to nucleophilic attack. Okay, so what about ligand close packing? What does this mean? When I talk about a ligand, I'm talking about the atoms that are bound to the central atom. So we're going to use the distance between the outer atoms as a guide, and the molecules with the same central atom have the same non-bonding distances that occur between outer atoms, even though their bond distances or angles to the central atom is going to change. So let's have a look at the example that's given over here. So what we see is that we've got, in this diagram here, we have 4 fluorine atoms bound to a nitrogen, and the distance between this fluorine here and this fluorine here is a distance of 212 picometers. Okay, now what happens is we now look at NF3, where we have this large lone pair of electrons, and we find that actually not too much happens in terms of the distance between the two fluorine atoms, but what will happen is that the angle will change. The distance will remain the same, but we're going to find that this angle over here is probably going to change quite significantly. Okay, so let's construct it, and if we use a Pythagorean theorem, you find that this distance here, 212, if we divide it by 2, we make a triangle. You can see it's roughly a triangle, so from this point we have the triangle. You can see the triangle. And if we take this midpoint distance from the center of the fluorine atom down here, you will find that this is now 106, 106, making 212. Okay, by Pythagoras, we were able to calculate the hypotenuse, and you'll find that you see that this distance theoretically is 130 picometers. How did we get that? If we have a look here, you will see that we can work out the angles, if we're given the angles, and you were able to calculate the experimental distance as, or the actual distance as 130 picometers, and we find that if we measure it experimentally, it's 136.5. So how these atoms here, we call them ligands because they're bound to the central atom here. How close do they pack? It all depends on the amount of electron density, and it also depends on the electronegativity and the atom size, as I've explained already. Okay, what about polarity? All right, you guys know something about polarity, and we know that bonding of atoms with different electronegativities result in polar bonds. And the larger the difference in electronegativity, obviously the more polar the bond. So polar molecules are going to interact electrostatically. They're going to move themselves due to the attractive forces, and because of this, they cause higher boiling points. This is measured experimentally by determining the dielectric constant of the molecule, and we can see what the net dipole moments are for the examples that are given in the slide. So for ammonia, this is ammonia, okay, and we've got water, and we've got NF3. You can see that the net dipoles change depending on the polarity of the bond. Remember that the lone pair of electrons doesn't really indicate anything significant there. Okay, so molecules with symmetrical structures can be as a whole non-polar, but they may contain polar bonds. They may have very small fluctuations in their electron densities, creating temporary dipoles, which then you know as London or dispersion forces. Okay, so the effects are more noticeable in molecules with a larger number of electrons. So for the three examples that are given on the slide, we've got methane, we've got carbon tetrachloride, and we've got SO3. Okay, and essentially you'll find that all three of these have a zero net dipole, but you'll notice that each of the bonds are polar, because carbon and chlorine, for example, are different electronegativity. So the direction of the bond polarity is different between carbon and hydrogen as opposed to carbon and chlorine. So even though we get a net dipole of 0, the bonds are still polar. And then lastly is a very unique situation which we know is hydrogen bonding. These tend to increase boiling points, and the explanation is simply because of the polarity of the bonds. Okay, so there's interesting attractions between, in this case, these are two water molecules. So you'll see between this oxygen and this hydrogen, we have a dotted line. This is actually the hydrogen bond, okay, and it's of significant strength such that it causes increase in physical properties. So it will affect melting point, it will affect boiling point of various properties, and they tend to hold the molecules together. So hydrogen bonding is a very unique situation, and it's very interesting to actually study this. So this concludes this particular section on the effect of electronegativity on and atomic size on bond and angles and bond strength and polarity and other forms of bonding.